you can look up that S-alanine has a specific rotation of positive 14.5 degrees. When you measure a sample of alanine, you get an observed rotation of positive 3 degrees. What does that tell you about your sample? Is it one pure enantiomer or a mixture of enantiomers? And what does the observed rotation tell you about the balance of each enantiomer? This is where optical rotation becomes really useful. Hey there, ninjas. In a previous video, we talked about how optical rotation works and what a polarimeter measures. If you'd like a refresher on those topics, I have that video linked in the description below. In this video, we're going to answer the question, what does an observed rotation tell me about a mixture? Because in real life, especially after running a reaction, your sample is almost never one pure enantiomer. One of the easiest ways to understand optical rotation of mixtures is by using a number line. S-alanine has a specific rotation of positive 14.5 degrees. Therefore, by definition, its enantiomer R-alanine has a specific rotation of negative 14.5 degrees. Each end of the number line represents a pure enantiomer. So what happens in a mixture? Recall that in a polarimeter, plane polarized light interacts with each chiral molecule and rotates the plane of polarization ever so slightly. And each enantiomer rotates light the same magnitude but opposite directions. In this example, the S enantiomer rotates the light clockwise and the R enantiomer rotates the light counterclockwise. Just recall there is no correlation between R and S and plus and minus. So if I have a mixture where both enantiomers are present, every time the plane polarized light hits an S molecule, it'll rotate the light slightly clockwise. And every time it hits an R molecule, it will rotate that light back in the counterclockwise direction. And because those interactions are equal in magnitude and opposite in sign, they cancel each other out completely, unless one of the enantiomers is present in excess over the other. Let's imagine my sample is composed mostly of the S enantiomer, with a little bit of the R enantiomer mixed in. As the plane polarized light passes through that sample, all of the S molecules will rotate that light in the clockwise direction, and the few R molecules will rotate it back in the counterclockwise direction, but only slightly. So at the detector, the overall result is still a positive observed rotation, but not as positive as the pure enantiomer would be. And from that concept, we get three very powerful rules. The sign of the observed rotation tells you which enantiomer is present in excess in the mixture. For this example, if the observed rotation was still positive, there is more S in the sample than R. If the observed rotation was negative, we'd have more R enantiomer in the sample than S. Second, the magnitude of the observed rotation tells you how close that sample is to being a pure enantiomer. The closer the observed rotation is to 14.5 in either direction, the more the sample is closer to being a pure enantiomer. The closer the observed rotation is to 0, the closer it is to being a 50-50 mixture. And rule number 3, observed rotations must fall in between positive and negative 14.5. We should never expect to see a rotation of positive or negative 20 for a mixture of alanine, because 14.5 degrees is the maximum rotation for a pure sample. So let's say you run a sample of alanine through the polarimeter and you get an observed rotation of negative 12 degrees. On the number line, that's very close to negative 14.5 degrees. That tells you your sample is mostly R, but not perfectly pure. There's still some S enantiomer in that mixture that's canceling out some of that rotation. Back to the example at the beginning of this video, perhaps the observed rotation is positive 3. That's a positive number that's closer to S than R, so our sample is enriched in the S enantiomer, but positive 3 is very close to 0, suggesting that the enantiomers are present in almost equal amounts. There is a slight excess of the S enantiomer, but it's fairly close to 50-50. The big question then is, what if the observed rotation is actually 0? It does not mean that alanine is achiral. We discussed in the previous video that achiral molecules do not directionally interact with plane polarized light, and achiral molecules have a specific rotation of 0. But alanine is clearly chiral, so an observed rotation of 0 does not make it achiral. Instead, remember the cancelization principle. As the plane polarized light passes through the sample, every S enantiomer of the molecule rotates the light in the clockwise direction, and every R enantiomer of the molecule rotates the light in the counterclockwise direction, the same magnitude. An observed rotation of 0 suggests that every clockwise rotation was exactly canceled by a counterclockwise rotation, which should only happen if the R and S enantiomers are present in equal amounts. We have a special name for this. When we have a perfectly 50-50 mixture of enantiomers that gives an observed rotation of 0, we call that mixture racemic. A racemic mixture, or a racemate, is defined as a perfectly 50-50 mixture of enantiomers. Let me be perfectly clear about 3 points of that definition. A racemic mixture is precisely a 50-50 mixture, not a 49-51, not an 80-20, precisely 50-50 to be racemic. Secondly, it's precisely a 50-50 mixture of enantiomers. We cannot call a mixture of diastereomers a racemic mixture. Enantiomers only. And third, a racemic mixture does not mean the molecule is achiral. It is chiral, just both enantiomers are present in a perfect 50-50 mixture. Therefore, the sample as a whole shows no net rotation because of cancellation. One important point to make is about mixtures of diastereomers. Glucose and galactose are diastereomers. Some, but not all, of their stereocenters change their RNS configuration. We've seen earlier that enantiomers have equal magnitudes of optical rotation, but opposite signs. That is not true for a mixture of diastereomers. For diastereomers, there is no relationship for the optical rotation. Look at these two molecules. They're both positive optical rotations. If I know the specific rotation of one diastereomer, I cannot conclude anything about the optical rotation of another diastereomer. So be careful with diastereomers. They are outside the scope of the optical rotation discussion. To summarize, a sample of a pure enantiomer will show the maximum specific rotation for a chiral molecule. Measuring the rotation of a mixture of enantiomers will give some partial cancellation of that rotation. The size of the observed rotation will tell which enantiomer is in excess, and the magnitude of that observed rotation will tell you how close we are to being a pure enantiomer. And a mixture of enantiomers with an observed rotation of 0 is a perfect 50-50 mixture we call a racemic. This is a good qualitative understanding of mixtures of enantiomers. But there is a deeper question. If my observed rotation comes out to be +3, how do I calculate the exact ratio of the enantiomers in that mixture? That is a topic called enantiomeric excess, and that will be the subject of the next video. Let's stay curious and keep exploring together.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.